Okay. So, we are discussing the small signal description of various amplifier types. Let us start with type 1, wherein what I have drawn above is what I claim to be a realistic description of one kind of amplifier. In order to motivate what kind of amplifier this is, we will first look at an ideal version of the same circuit. The ideal version of the circuit drawn above is shown below, and in order to get the ideal version, we basically set Ri to infinity and Ro to 0. Is that right? So, somebody asked the question as to what about Rs. Rs itself is something that belongs to the source of the signal. So, in this case, for example, I have a microphone. The microphone connects to the input jack of the computer. The microphone has some resistance, right? So, let us not go to that level of idealism where you assume the source also to be ideal. Actually, you do not need it. Why do you not need it? Sorry? Exactly, right? The moment you make, so if I call that current as I1, right? The moment I make the input resistance Ri infinity, I1 is 0, correct? Which means whatever the value of Rs, it really does not matter, right? And that is the reason why for many amplifiers you want the input impedance of the amplifier to be as high as possible. In fact, we have discussed the op amp, right? In the case of the op amp, what did we say? Just as an aside, for the op amp, what did we say? We said that we want Rin to be infinity, or an ideal op amp has these properties. R out is 0 and the gain A is infinite. Okay. That was what we had modeled as an ideal op amp, right? Okay. So, now does this look like an amplifier? Does the circuit which I have drawn and called as the ideal situation, does it look like an amplifier? If I choose my K to be greater than 1, then I am going to amplify my input signal. So, what do you think K can be called as? K is gain, but something more? Under what situation is K the gain? Right. So, when the input part is effectively open circuited. So, this K sometimes is called as the open circuit voltage. The open circuit is the fact that input port of this amplifier looks like an open circuit. There is no current that flows through the input port of the amplifier. Okay, we are going to have that in the video also. It's all right. Okay, so can you tell me what now? Can you give a name for type 1? What say? No, somebody said something. It is a voltage controlled voltage source. Correct? It is a voltage controlled voltage source. All right. Now, let us go back to the real situation, and I asked the question as to under what situation does the real description of this amplifier qualify to be close enough ideal. The question? So the question is, can you call the real distribution as ideal or to ideal? Right? When can you do this? Basically, if Ri is greater than Rs, what about the output? So you are happy with this Ri greater than Rs? No. Okay. I am telling you it is this. See if you can justify it yourself, otherwise I will justify it. What is Vi in terms of Vs? Ri divided Rs plus R times Vs. In the ideal situation, what is Vi? Correct? So now to go now if you want your real situation to look like the ideal situation, what should be the condition on Ri and Rs? If Ri is much greater than Rs, basically drop this Rs from the denominator and you will get back your real situation. Alright? Okay. What about the output situation? Okay, let us write down here first. For ideal situation, what is VO? So VO is basically K times Vi, right? And in this situation, your VO is going to be RL divided by R naught L times KVI. So you need, so your RL be much greater than R0. Okay. So what this is telling you is that if you have a small signal incremental picture such that Ri is much greater than Rs and RL is much greater than R0, then you can call that particular amplifier as a voltage controlled voltage source. Okay. Let's now go to another type and then it will become clear to why I am saying this. Okay. Just to complete this, in this particular case of RL being greater than R0, you can actually drop R0. Okay. So now let's go to the next type and become clear as to what I said. So I will start with the same situation. Okay, let me start with not this one. Sorry. Let me start with this. Okay. Let me start with this. This is going to be type. This is going to be type 2. Is that type 2 or have I called it something else? No, 1.5. And this is clearly not going to be a volt control current source. Let me just take this situation and we'll take this amplifier which is real, which is a circuit which demonstrates a real voltage source, right? And then we'll see if we can do some change to this and make it appear like a kind of amplifier.
How did the RA become a VA become K times?
Yes. How did? Yes. So good question, right? So we have this dependent source and I happily wrote down that the value of the dependent source is K times the original voltage or the input voltage VI, right? How is that happening? How is that happening? Now, we will see how that happens in the next few classes. Okay. So, you need an is this an active device or a passive device as drawn? It's active, right? Why is it active? Sorry? Yes, it's a source, it's a dip source, so it's an active device, right? So you will see that the devices that we use, the real devices we use in order to facilitate this particular equivalent circuit will all be active devices. So we will use a transistor, right? So the transistor, when operate in a certain regime, will behave like this like this dependent source. Okay. Now let's go to the next. So what I am doing now is to start with the same circuit and see if we can find a different situation under which you can call this circuit by a different name, right? That will still be the real version of that circuit, and then we will do we did last, which is then to make the ideal version of that circuit, right? Just as we did here. I started with a real circuit which I claim describes an amplifier, then we one limit of the resistances and got an ideal situation, and then I told you okay, you don't really need to go to that extreme limit, you can have a slightly more engineering limit, which also allows you to describe this real circuit as a voltage controlled source. Okay, alright, now let's take this. Now all of you will know what I am doing, or at least can guess what I will do. I am going to circle this and ask you to tell me what I will do, right? So what am I going to do to that? I am going to convert that into, I will convert that into a current source. What should be the current source? Vs by Rs. And what should I put in parallel? Right? And some other stuff I am not going to change, so let that still lie. This is going to be your. What about output? Somebody, what I can do to that? Well, I have something to the input, so I want to do it to that one also. Well, let me take this and then we'll make the other two comments. Okay. So I'll do the same thing that we did here. So basically I convert this into a current source, right? Usually current source direction is drawn this way. It's okay, conventionally it's downward, that's all, right? Though you were to convert this, you might have put it in the upward direction, but that's okay. And what should happen next? Where will that O come? That will be your RO, and that will be your. Okay. So what have I done? I have just come this circuit to this circuit by source transformation, right? Nothing very fancy. Okay. Now let me take the. Now let me motivate this particular equivalent circuit with the current sources can actually be looked upon as a current controlled current source. Okay. If I want to make this circuit current controlled current source, what should be the ideal situation? First, we'll just take this here, keep it. So, what should I do? So, if this is an ideal current source, right, what should happen your what should Ri be? So, the ideal one of this would be that Ri is if I take the situation of Ri being 0, okay, then all the current that is flowing from this will go in here, correct? Similarly, output, what should RO be? Right? If I take RO to be infinite, all the current that is flowing like this will go that way. Nothing will flow through RO. So that will become an open circuit. Now, can you tell me what this would be? This dependent source. If I call this as say I2 and this is say I1, then what is this going to be? K times I1. Okay. So, this is now a current source, right? So, what have we done? We have started off with some circuit, right? Then we did this source transformation of the input and output, and then I said let me take an ideal version of this. So, I said Ri 0 and I said Ro is infinity, and then I got this ideal current control current source. Okay. So, now let's just like we did it for the previous situation, you can compute story. Let me not write that again. I am going to put that here. Okay. So, can someone tell me if this happens? So, when can you call this real circuit, right? When can you call real circuit as being close enough to ideal? So, your I must be less than Rs, correct, and your Ro must be greater than right. So, now just spend a minute and look at the first situation. When I had what is it that we are trying to do? We have some circuit, right? We have circuit which looks like an amplifier. Under one limit of the input impedance being much larger than the source impedance, under one limit where the input impedance is much greater than the source resistance and the output resistance is much greater than and the load resistance is much greater than the output resistance of this amplifier, you can call this real system or real circuit as a control voltage source. Okay, that's one kind of amplifier. Under another limit of the input resistance being when Ri is less than Rs and when Ro, right, much greater than RL, the same system can refer to better as a current control current source. Right, starting with the same system, the same real system can either be modeled as a voltage controlled voltage source or a current controlled current source, depending on the relative magnitudes of the various impedances involved. Okay. The following question: can I take an ideal voltage controlled voltage source and convert it into ideal current controlled current source? Think about that. The question I am asking is, can I take an voltage source and present it as an ideal current control current source? What's the answer for this? Yes, no. How many say yes? Okay, how many say no? And others don't care. The answer is no. And why is that? Can you justify at least the answer? Not Prasanna. Don't pulling his leg. I am saying it is no. So give me the answer for no. Can you do a source transformation? So if voltage source like this, right? So you have a voltage source, some resistance, then becomes a source with the same resistance in parallel, right? That is. But what happens if you have a where you have just voltage source? So this is a real voltage source. This is the ideal voltage source. This is the real current source, and you will have ideal here. 1 minute. So can you go here? You can't, right? You can't, right? So that's why you can't take an ideal voltage controlled source and represent it as a current controlled current source. However, if you take a real voltage controlled voltage source, you might be able to say that it is a current controlled current source if the various impedances, if you change the relative magnitudes of source and the input resistance and the load and the output resistance. So the same system for one kind of source can behave like a voltage controlled voltage source. For another kind of source resistance can behave like a current controlled current source. Right? Okay. Now that we have done type 1, type 2, I think you can guess the other two. What would they be? Right. So now that we have done type 1 and type 2, we can now do type 3. Right. And which one do you want to do as type 3? You have to draw, yes. You want to copy, right? So let me this. And let us say that we are in the situation where let's take the situation where Ri is much greater than Rs. Right? However, your R0, that was small r, right? However, your R0 is much greater than RL. What does this mean? Right? This will become, this would then make a voltage controlled current. Right? And how would that look? The ideal version of that? The ideal version of that would like Vs, I have an RL. Right? There is no Ri because Ri is much greater than Rs. So in the limit, Ri is going to be infinite, right? And on the other side, I'm going to take this limit of R0 much greater than RL, right? So I can basically convert this to a current source and directly feed the load. Okay. And plus minus is going to be Vi. Correct, and this is going to be your I0, I out, and what is this going to? This is going to be some G times Vi. Can you give a name for this device? Huh? So the another name for this thing is called transductance amplifier. Right? So G is a conductance, right? However, it is a conductance relating your input port and the output port. So that's why the trans, to connect between input and output, and that becomes the transconductance amplifier. Correct? And then now that you have this, I can go to the next type, which will be, which one have we left? Type would be current control voltage, right? And so again, let me start with the same thing. Which one? I've taken this and then I made this change and I've got this, right? I think that's enough for this. Okay. All right. Now, what should I do? In what limit will this circuit have like a CCVS? Ri must be less than Rs and R0 must be, think, yeah, if it's that. So just in your mind, just convert it to a voltage source, convert voltage source to a current source and see under what limit does it become an ideal current, right? So if you take this combination, this dependent voltage, this resistance, you will get a parallel resistance of R, right? In the ideal situation, you don't want any current to flow through the R0, you want all the current to go out, which means that R0 is infinity, right? So which means, no, sorry, I want a voltage source on the output, sorry. So whatever I said, you do it to the input system, right? Huh? So no, basically you take this. No, what I've written is correct. What is correct? So you see, Ri greater than Rs. This is Ri less than Rs. So the Cc becomes Vc. And then Ro greater than RL. This is Ro less than RL for Vs. Okay, it's like a dual. Right? And how will the ideal one look? So you will have control, have here, and then I'll have a short there. Right? Now, so RO less than RL, in the ideal version this will not be there. Did that in the previous one also? Yeah, okay. Okay, now can you tell me how I will name this? Yeah, but with that, this is the current, all of this current is flowing, let me call that as I1, right? And what is this? This is a voltage source, this is going to be some, so we have, so what should I use? If Z, okay, Z is decent, okay, it's a good one actually. Let me call that as times I1. And why did you say it is Z? Because, yeah, right, because I have voltage here, right? This is my voltage, and the voltage is related to a current. So this is effectively has units of resistance or impedance. Okay, some people call it a trans resistance amplifier, but I think a trans impedance amplifier is the name. We'll call trans impedance amplifier. Okay, so I hope you have got the take home of what we have done so far. Basically, any real circuit, depending on relative magnitudes of the input impedances of the amplifier block and the resistances of the source and the load, you can classify it as one of four types, right? But if your circuit was an ideal corresponding to one of these types, you can't classify it as any other type. If it is a real one, you can move it around depending on what the values are. If it's an ideal one, it's just stuck there. Okay. Now, let's just see how one of these are implemented. Okay. And which one do you think would be the first one that I think about? Okay. Just to put it in perspective, the current control source. Okay. So if you remember, we had a bipolar transistor. In a bipolar, how did we rate the quantities? I said this was base current, that was the collector current, right? And yes, and this is your collector, this is your base, this is your emitter. How did we relate various things? Yes, and the other relation, you said IC is beta B. Correct? So, many BJT based amplifiers will to look like current control current sources. Correct? However, you can make things also from this. I am just saying that many of the BJT amplifiers will look like current control current sources. Finally, because the BJT itself is not it has its input impedance and stuff like that is not either 0 or infinite, it has some input impedance. So depending on how you connect it, right, it will look slightly different. So basically, okay, let's leave it at that. When we come to the BJT circuits, it will become clear. Okay, but the BJT itself is a current controlled device, right? Depending on the input current is, you get a different output current. All right. Okay, then how about this? So we looked at MOSFET, right? In the we call this gate, we call this and this the drain. And if you remember how to write the ID, was I a function, what is the current? Gate current is 0, right? In an ideal MOSFET, gate current is 0. So which do you think it should be? Right? So that's why I have drawn it on this page. So many MOS based circuits look like voltage controlled current source. Sorry? They are. No, I didn't get your question. Yeah. See, again, let's just for now, let's not go into the edge case. Okay. Let's say that the MOSFET is a voltage controlled device. The output current of a MOSFET is controlled based on its input voltage. Yeah. Depends on? It does, but you're looking at what is the dependence on between output and input. Okay. So henceforth, what we will be doing basically is that we will take, for example, one kind of amplifier topology, right? We'll take, for example, what is called a common emitter amplifier, right? So we'll take, this is the first one that we will study, okay? And this many things clear. A parallel to the common emitter amplifier B1. So this is the BJT amplifier. What would be the MOS equivalent be? So see how I have drawn it. Emitter is drawn down, source drawn down. So it will be a common source amplifier. Okay. Similarly, we have common base, and that would be a common gate. And we will have a common collector, and we will see that be similar to a common drain. Okay. This will be the agenda for the next few weeks. Okay, because each of understand what is its input impedance, what is its output impedance, why is it good, why is it bad. Okay, and is where you get confused. So we might not do everything in the same level of detail. We'll do it for the common emitter and the common source. Okay, those are the most useful of the amplifiers, and the others I'll leave as tutorial problems as usual. Okay, all right. I'll take another 5 minutes and then we started. So okay. Don't listen. It's anyway recorded. Listen. Huh? So it's okay. Let's start ideal model. Okay. Because we have done this already, right? And let me call that the gate and this the source. Well, I want you to calculate this and come. You have done this earlier, but I want you to recalculate or get it from your old notes. Okay? Okay. Somebody who remembers what is ID equal to? Good point. Under condition. Okay. So as Prasanna has asked, many conditions. First is, let me say VS, okay, is less than T, where V is called Thevenin voltage, no, threshold voltage. T is used in many places Okay, some places it is a thermal voltage, some places it's a threshold voltage, some place Thevenin voltage, right? Just like there are many Madhav, but refer to the correct Madhav, refer to the correct voltage, right? Okay, so when VGS is less than VT, what is ID? We have done this earlier. 0, right? In the simple model. Okay, then when VGS is greater than, think and answer please. This is not a digital circuit. It's going to be? Yes, yes. So I'll give those conditions. Okay. So you have this. That's why I'm writing down. So I don't. VGS minus VT into VDS minus VDS good square by 2. This is the situation where VGS is greater than VT and the other way around, and VDS less than okay, and finally into VGS minus VT whole square 2 when? So it is the thing when VGS is greater than VT. VGS is greater than VT and VDS is greater VGS VT. Correct? Okay. And I don't think we did this earlier. There's one more term here, which is 1 plus lambda VDS. Correct? Okay. So what I want you to do is to plot this come. Okay, I want you to this and come to see how it looks.